Morning. My name is George Bekmezian, and I have the opportunity to share some of this information with you this morning. I'm a little surprised at the number of people that are here because there's a badge hacking session going on, and if I was not presenting, I'd probably be there. So I guess you guys might have a little bit of interest in DNS, but I'm going to tell you just a little bit about myself before I get into the topic. First of all, the father in this story is me. This was just a couple of weeks ago. You can check it out on KSL. But I'll tell you a couple of things. What they say about make sure that you meet in a public, well-lit place when you're doing a KSL transaction is true. And it's important to carry with you if you're going to do something shady like this. So anyways. So that's me, and then another thing about me, this is me as well. I'm running for a Utah House seat in Harriman District where I live. So a couple of personal things about me. Thank you. And so I work for Cache Valley Electric, the technology division, and I've been there about 3 years. I've been working in this industry for, 20-something years. I've worked a lot in DoD space for a long time. I worked supporting an MCI network in San Diego. I've supported organizations in Northern Virginia. Some I can't mention, some I can. White House Communications Agency is on the list of organizations that I supported. So anyway, so that's a little bit about me. This session, there's a lot changing with DNS and privacy on the internet. And so what I want to talk about today is how those changes are affecting our ability to provide content filtering and security. But in order to do that, I want to walk us through a little bit of DNS to make sure that we have a good foundation. But I'm not going to get into a lot of details about the protocol, but just enough, hopefully, that everybody understands. And then we'll talk about the privacy concerns associated with DNS, and then get into some of these DNS SEC, DANE, DNS Script, DOT, DO. So a lot of these things. And DNS over quick, I took some of those slides out because I'm concerned about time, so we'll see what happens. And then I have a little demo if I have time. I'll show you DOH that way, and then we'll talk about at the end, okay, well, what does this all mean? TLS 1.3, how many of you guys are concerned about TLS 1.3 out here? So there's a few hands. How many of you guys do content filtering leveraging DNS today? Okay, that's a good, maybe a quarter of you. So, all right, let's go ahead and get right into it a little bit. So DNS is something that's been around for a long time, right? It was over 30 years, and it's crucial to be able to have something to resolve names to IP addresses. And so, but when DNS was first, ratified and implemented, privacy was not something that they were thinking about. And so we're here today talking about this because hindsight is 2020, but DNS runs over UDP. I think a lot of us know this, and it's in clear text. But why is privacy even important when it comes to DNS? And we're going to talk about that in just a second. But just real quick, for DNS, privacy is important because not only are we resolving IP addresses, DNS also carries other information today, right? So, for example, when there's been some additions to DNS. These text records, for example, are used for things like I want to secure email transactions or email communication. So how do I validate that an SMTP server that is sending email from a certain domain is actually supposed to be sending email for that domain, right? So we leverage text records in DNS to pull down a list of IP addresses of servers that are valid, right? So those kinds of things. So DNS is used for a lot more than just name resolution. Right? And so this is how a lot of times people think about DNS, and you think this is how DNS works. The client on the left is making a request to go to cv.com, let's say, and you make that request of your recursive DNS server, either on-site or the ISP, but that DNS server will go to the root server and ask, where is .com live? And that server responds, and then the server will say, okay, where does cve.com live? And then that server responds with the DNS server that cve.com lives on. And then finally, the authoritative server that can respond for cv.com will give us an IP address for www. But DNS doesn't exactly work this way, and we'll talk about that in a little bit. But before that, I want to talk about limitations of DNS. Again, DNS being over 30 years old, right? They didn't know back then what we might be wanting to do with DNS. And so the protocol itself is, the original protocol itself is pretty much exhausted as far as space left in the headers and the payload. And it was a limit of 512 byte payload. And so something had to be done because there's just no room to put anything else in here. And so there came EDNS. And EDNS was ratified, and it extended DNS and allowed a negotiation to take place to be able to send larger payloads in DNS packets and without having to revert to TCP. So it didn't fundamentally change the way DNS works, but it extended DNS in that way, right? See, I think we share slides later, but you can read the slide later if you want. But basically, there's an OPT record on the DNS server that the client will look up and say if that record exists, then it knows that the server can support EDNS and expanded packet sizes and stuff like that. Right. And when EDNS came out, there were firewalls knew that DNS by standard was 512 bytes UDP packets. Well, now with EDNS, firewalls had to be modified to inspect the traffic and to learn what the negotiated payload size was in order to make sure that if we negotiated a 3,000 byte payload, then the firewall shouldn't allow the server to send more than that, but it also should not restrict the traffic to only 512 bytes, right? So firewalls needed to be more intelligent in understanding this protocol as well as a result of the EDNS enhancements. So then EDNS comes out and some interesting things start happening. One of the things is because we can extend DNS with more fields now, ISP started using EDNS for maybe to share the MAC address of the client so that they can provide parental controls. All right, so that's one use case of EDNS that maybe wasn't originally predicted, but ended up happening. And then what happens is now we start leaking more data to the network, right, to the public internet. We don't know whether it's your ISP, whether it's any node in between your ISP and authoritative name servers. We're leaking information that is in clear text. And not only that, the way DNS really works is, remember originally I had .com in the first recursive request. Well, really what DNS does, the recursive DNS server does, is it sends the entire request, www.cve.com, to the root authoritative server, even though that server doesn't need all that information to tell me where .com lives, right? Similarly, to the next level server, it's sending the entire lookup, right, request, but all the second level DNS server needs to know is cve.com. So we're leaking a lot of information, and if we don't trust the carriers, they can be collecting that information. They know our source address, and who knows what they're doing with that information, logging it, using it for whatever. And then there was an enhancement. Another one that leverages EDNS is the client subnet within the DNS request. Anybody think they know why it's important to be able to share the client subnet in DNS when you're doing name lookups? Well, think about content delivery networks, right? So here's an example that I'm gonna run through. Let's just say that we have a client that is living in Sweden, and that client's recursive DNS server is pointing to an ISP in Germany for some reason. Then when the lookup happens, then that ISP will request the resolution for www.example.net, but what happens is the authoritative DNS server for example.net sees the source IP address that's coming from an IP address in Germany. And so it says, okay, I know that there's a content delivery node in Germany, and then it replies with that IP address, gets back to the client, and all of a sudden the client is streaming that media from Germany. And it may not be the best experience for that client, right? So with the extension that shares the subnet of the client, what happens is the client again makes the request for that IP address, and then that recursive DNS server sends the subnet of the original client where it's coming from. So now the authoritative name server knows that that client is coming from Sweden, and so the response can be more intelligent and say, okay, since the client is in Sweden, I will give you an IP address for a node that resides in Sweden. And so now it goes back to the client, and the client is streaming his data or her data from a more geographically friendly place for him. So the experience ends up being better. Again, so good reasons for these enhancements, right? It improves the experience for the end user, which is a good thing. But there are some concerns, because while we were in flight, now we are sending in clear text a lot of metadata, a lot of information, and the question becomes, even at rest, what happens with this data? How many ISPs, how many DNS servers, DNS providers are collecting, logging? How long are they logging that information for? And nobody knows. But we're going to focus today on the in-flight portion, right? How do we secure and minimize the amount of information leaked? And this is a problem that the internet gods are trying to solve, because they care about our privacy. Sometimes they care about our privacy more than they care about our security, but that's okay. That's our job, is to make sure that security continues to happen. So there was an RFC, it was RFC 7816, and what that did is, it's not a standard, but it's just kind of a guideline that says, hey, when we're doing DNS lookups, let's send the minimal amount of information we need as a best practice so that we minimize the amount of information that we're leaking. And you can go read that. It's pretty good stuff, actually. And there's another reference here on DNS privacy, and that's a really good resource too. It talks about a lot of privacy issues, encryption issues, and just help you get deeper into this subject if you're interested. But if your resolver is implementing these best practices, then it will actually act the way we talked about at the beginning, where it's just sending what's needed per authoritative server, instead of blasting it with a fire hose with all information. Right? All right. So now we're going to get into DNS security. One thing that's interesting is, a lot of times people hear DNSSEC and they think, great, DNSSEC makes everything secure for me, and there's nothing else to worry about. How many of you guys here manage DNS? Anybody in here? There are a couple of. How many of you who manage DNS have actually implemented DNSSEC? One. Good. So I did some research online, and it looks like DNSSEC is like, the numbers are not that clear because there's not a lot of authoritative information, but what I glean from it is maybe 3 to 4% of domains actually have implemented DNSSEC. So it's really minuscule, but we'll understand why as we go through this presentation. Right, so then, DNSSEC will provide authentication and integrity, but there's no encryption. And so the encryption piece is important for privacy. Authentication and integrity is important. It's a good thing, and we want those things, but it doesn't solve the DNS privacy problems. But we'll talk a little bit about how this works. So DNSSEC, how does this actually work? We have a domain, and we have a record in our domain, and that record gets signed by using a server key. The one nice thing about DNSSEC is there are no certificates, right? So anyway, so that record gets signed by a server key, and the server has a public key that it publishes, and so you can query for the public key, and then you can look to see if that record is actually signed by that public key. That's great, maybe, but what do you think the problem might be with this model? Right? How do you know whether that public key is actually valid, right? Or it comes from that domain because it's hosted on the same server. So then we think, okay, and how do we solve the problem of rotating keys too? If I rotate a key, then the public key has to change, and you could have thousands of records that you have to re-sign, and anyway, so that can get messy. So then they thought, okay, we have a public key that signs, we have a private key that signs all of our records, and we have a public key, but how about if we add another layer to it? We have a zone signing key that signs records in our zone, and then we have a key signing key. So the key signing key could be a larger key, more entropy, and doesn't get rotated as often, and then the zone signing key would be getting rotated at some interval because it's being used a lot more often, and so there's more data out there to be able to maybe solve for the private key for that one. Anyway, so what happened in this model is great, except if we look up here, the arrow circling back on itself, that key signing key is self-signed. And again, it's hosted on itself. And so if my DNS server is the authoritative of not only the content, but of the signatures and the keys, then it still didn't really help a whole lot about validating integrity, right? So we needed one more thing to happen. And what DNSSEC actually does is it creates a hierarchy, and so there's this idea of a delegation signer. So .com would be a delegation signer for CVE.com, and then there's a root above .com that's the delegation signer for .com. And so now we have the zone signing key that is signed by the key signing key that was signed by the delegation signer. And so that there's a chain, went too far. So there's a chain all the way up to the root key. And your resolver only has to have one certificate that's pre-installed, or not certificate, one public key that's pre-installed, and that's for the root. So if it can validate the root key is actually valid, then it can use that chain of trust all the way down to the bottom, right, to your zone. Well, that's all great, and the problem is, like I said earlier, it hasn't been implemented widely enough. And it's been a long time, actually, since DNSSEC was ratified. But here, earlier this year, there was ICANN, the Internet Corporation for naming and numbering, they assigning names and numbers, they decided that there's a serious problem because of the lack of integrity in DNS. It is leading to more and more DNS attacks, and so they're encouraging people to fully deploy DNSSEC. Right? So there's a nice little tool. If you go to dnsviz.net, you can put in a domain, and here I put VeriSign in. By the way, it was really hard to find a domain that was actually signed, that actually has DNSSEC implemented. I tried some bank sites, and I've tried some technology company sites, and a lot of them have not implemented DNSSEC. But I know this is small. You can go look at it later on your own too, but these arrows down here that are green indicate that there's a trust between each of these zones. And so this shows you all the details, key signing keys and their public keys, and anyway, the whole chain all the way up. So that's great. But with DNSSEC, right, what did we solve? Well, we authenticate the record, which is really good, and we make sure that it hasn't been modified. Again, really, really good things. And it's easy to do because there are no certificates involved, which again is a benefit. But it still doesn't solve our problem of encryption and privacy. So now we get to a little bit more interesting topics, right? This idea of, okay, because it's important to have integrity because of what we talked about earlier. If you're using the DNS server, right, so Dane, so here, I don't know if a lot of you guys have heard about Dane, but domain authentication for named entities. What this does is it says, let's say it can be used for mail in this example, but it could also be used for any website. Just because I go to, say, let's say I go to ESPN.com, right? And I see the little green lock that says that one of my browser pre-installed trusted certificate authorities validates that site certificate is signed by something I trust. But it doesn't necessarily mean that it's signed by the certificate that ESPN.com intended for that site to be signed with. So anyway, what Dane will do is you can put a record in DNS and say, here is the signature of the certificate you should expect when you go to ESPN.com. And so that's another level of security, right, fidelity that says, or in Dane you could say, here's the certificate authority's signature that should have signed ESPN.com. So maybe ESPN.com should be signed by VeriSign, but it's signed by GoDaddy or something like that. And so that would tell the client that there's still something wrong, even though the URL and the certificate match, it's not the right certificate that ESPN.com should be using. So anyway, so Dane's a good protocol. It can help with integrity and security on the internet, but you wouldn't want to do this if you don't already have DNSSEC, right? Because you want the DNS architecture to be secure before you're going to trust DNS to provide security for other protocols and other traffic. And if you want to learn more about Dane, there's a really good video that goes into details on YouTube. Feel free to go watch that. And so we're gonna keep going to DNS encryption now, right? Because again, the internet wants privacy for people, and so DNS encryption is the way that we're gonna do that. But the solutions we're gonna discuss only address encryption between the client and that recursive server, not between the recursive server and the other authoritative servers that you might be doing lookups for. So I just wanted to point that out here. That's where we're going to focus, and we're going to start first with DNS Script. DNS Script is it's a good protocol. It's open source, it's free. It has a lot of implementations out there. You can go download, you can download application, you can download a library, and there are servers out there. For example, OpenDNS has a DNS Script support already. So if you have a client that does DNS Script, the server does DNS Script, you can have encryption then from client to that resolver. And it solves the problems of encryption and authentication, and it can actually coexist with DNSSEC. So there's no conflict there. Let's move on. So here's an example of how DNS Script would work, where you have an app, the browser or whatever. The app requests a URL, www.espn.com, and that URL, that browser will actually still use the OS and to do the resolution, but the application you have installed, your agent, would actually be a shim in the OS. So the OS is aware of this. The OS sends that request to the application, and then the application goes and does the lookup. And so that's one model. And then if we look here, it's kind of hard to see probably a packet capture. But the thing to note on the packet capture is that the traffic is not standard DNS. You don't see DNS. It's encrypted over UDP port 443. So, but also you will see that the site is still blocked, despite the fact that we can't see the content of the request. Right. So then we go to DNS over TLS. So DNS over TLS is the standard, and we can do either DNS over UDP, right? So TLS, or you can do, or that's called DTLS, or you can do DNS over standard TLS. And so this standard, the DTLS standard isn't really implemented. There's not any implementation out there, but the DNS over TLS standard is supported already by, I think Google does this, CloudFlare, and so there are lots of open public implementations of DNS over TLS already today. And so they had to decide a few things, right? They had to decide whether they're going to use an existing port, like port 443, or are they going to do something different or something unique for this protocol. And in the end, they've decided on a port 853, and as hard as it is to allocate a port, they were able to do it for this protocol, which is a good thing. So we can identify that there's DTLS, or not, DNS over TLS happening in our network by looking at TCP 853. And also there's one other thing that I'll show you a little bit in a few slides that gives us an idea of DNS over TLS taking place. But the model for DNS over TLS is pretty similar. You have a client on your workstation or device, and the browser, it basically is the same model as DNS Script. But the one thing that could be different with DNS over TLS is a browser might natively implement that protocol so that it bypasses the network stack, right? So here's an example of an application, Stubby DNS, that anybody can download and test and validate what happens. But basically, you do a lookup using Stubby TLS, and you will see that the traffic, the name resolution is happening over the port 853. And the one thing that's important to note is in the packet, the TLS12 header, it actually tells you right there that the application is DNS. So it's more friendly for security or in content filtering to be able to identify that, and then you could block it if you wanted to, right? To hopefully they fall back to regular DNS or something you have visibility into. Well, here are some examples of public implementations of DNS over TLS. The one other thing to keep in mind is this list is constantly growing. So what that means is that right, if the the browser implements it directly, you lose visibility into it. But also, you can blacklist destinations on a firewall based on the known growing list of public resolvers that implemented DNS over TLS. The problem with that, though, is it's kind of like playing whack-a-mole, right? Because you might block the known servers, a new server pops up, and it's a losing game. So you're not probably going to want to play that game where you're blacklisting destinations to prevent DNS over TLS on your network. So let's now go to DOH, or DNS over HTTPS. This one is the more controversial one because the browsers, Chrome and Firefox, have native implementations of DOH already, right? And they can already bypass anything we're doing. But the good news is that they're not enabled by default yet. And there's a lot of pressure on those browser companies to be careful about how they implement this. And we'll talk a little bit more about that. But the nice thing about DNS over HTTPS is that it's really easy to implement. It's really easy for the end user. It provides them privacy, security, and of course, it means that as owners of the networks, it makes us completely blind to what they're doing if they do choose to go that route. And so this model will completely bypass the operating system stack. And so if the client is doing this, there really is no real recourse to stop it except for you have to inspect HTTPS or TLS traffic on your firewalls or on or explicit proxies. But we'll talk a little bit more about that too. And here, sometimes some people think, okay, here's an example in Firefox on how to enable DOH. And the first thing to note is down here where it says network TRR mode. That's where 0 is by default disable, and Firefox today is still disabled by default. Your mileage may vary though. If you look at your configuration, I'll tell you why in a minute. But the other thing too is down below a little bit, we can see where it says the network TRR URI. Well, that URI is telling Firefox, use this as your resolver for DOH. Okay, that's good. If we know that it's using CloudFlare and we own DNS for the first lookup, when the user looks up for CloudFlare's DNS server, we can block that request, and then the browser will never get CloudFlare's DNS server's IP address, and so then they will have to fall back to traditional DNS. But there's a field up here at the top where it says the bootstrap address. And so if somebody puts in the bootstrap address there, say quad 1s, then the browser will never do a traditional DNS lookup, and it will go directly to that DNS server to do its lookups. And now you couldn't block this behavior from a traditional DNS security perspective. But there's some good news. Google Chrome has said that they're working on implementing DOH in a way that is enterprise friendly. Because some of the problems with DOH are, first of all, imagine if I'm a user in your network or I'm an employee in your company and I have DOH. What if I want to look up an internal record, internal resource? If I have DOH enabled and that's a default behavior, it breaks me functioning, right? It breaks me working. And so that's potential help desk calls. And so nobody wants to have that problem, right? Well, Google is saying we're going to work with enterprises. We're going to have a way to have group policies manage this configuration. Also, what they're going to do is have a table of known DNS providers. So Umbrella, Google, Cloudflare, I'm sure some of the big ones at least will be on the list. And if those known DNS providers have equivalent DOH service, they're going to leverage that same DNS provider but using DOH. So that's user friendly, and it's it's a little bit better for the environment, right? But this is something that you can turn on and off right now if you wanted to by editing the flags in your Chrome browser. Okay. One thing that's really interesting about DOH is how quickly DOH went from a draft to ratified, right? In under, I think what is like under a year and a half or something like that. So this is another sign that the standards body and the people behind them are really serious about making sure that they're providing privacy for users. They feel this responsibility to do so, and so this was fast-tracked, and there's no reason to think that it's going to slow down. Right. Here are a couple of really recent articles just from last month, where we see that Chrome 78, they're playing a little bit of catch up, but they are catching up pretty fast with their implementation of DOH. And then Mozilla is already committed to slowly rolling out DOH by default. So this was last month they said that, but the default behavior is going to be DOH enabled. I don't know how they're choosing which users to enable it for, but so their testing is going live already, right? So again, regardless of whether or not what the default is, you can obviously as a user enable that for yourself. And so who thinks, is this scary or is it good? Or I mean, what are your thoughts? There's certainly reason to be concerned, right? Well, it's just kind of summary for a DOH is that it's great for an individual user. It's, if I'm just at a coffee shop or even at home maybe, I don't know, but it's really bad for enterprises and corporations, and even if you're providing guest services for somebody in your network and you're liable for what they do on your network, right? So it makes it really hard for you to provide a layer of filtering and security for them. And then the other thing is, if you could choose to play this whack-a-mole game again, known DOH services on the internet, blocking them, but it's futile because anybody can set up a DOH proxy, any IP address, and you're not going to win that battle. So what next, right? This is just the list of publicly known DOH servers, and this list is growing constantly. One thing that's interesting, I thought, one of those articles, it quoted this Paul Vixie, who is one of the founders of DNS, and what he said is, I'm just going to read the last sentence here. It says, DOT is a universal good. DOH will be a net harm, no matter what good it may do. So there's that whole contention between the privacy advocates and security advocates, and they're clashing, and they're trying to figure out where the happy medium is. Right. And then there are a couple of RFCs you can go read, talking about the risks and concerns of DOH as well. And one of those things, DNS was designed to be a highly distributed architecture, right? So DNS failure in one network or one service wasn't going to be a broadly impacting internet availability, service availability, stuff like that. But what's happened over the last maybe 8 years or 10 years is there's been a consolidation of DNS services, right? I think DNS had a pretty big outage. I think it was in the past year or something like that, and it took down some pretty serious services because so many people were using that service. And so this draft talks a little bit about the concerns of consolidation of DNS to a handful of service providers, and also talks about the concern, if we are protecting users' privacy by making sure that what they're doing isn't visible all along the path, is there not a concern that you're sending all that same information that you're trying to hide from intermediaries all to Google, right? And what is Google going to do with that information? They're certainly not going to not take advantage of it and try to make more money off of it, or make more money off of you too, right? So I'm not knocking Google. I'm just saying that we have to be careful about where we're sending our data. Just because the ISP is not seeing it doesn't mean that it's in a safe place. So, and then, so there's another idea that, hey, maybe we can give enterprises more control by having DOH be specified in a DHCP attribute, so the client dynamically learns the DOH server to use. But the concern there is if you have DHCP be hijacked for some reason, or somebody injects a response, then they're using encrypted DNS to a service that you have no visibility to, and you can't protect that user anymore. So again, people are trying to solve these problems for enterprises, but there's a tangled mess. There's a lot to consider. This is really good. So the Canary Domain idea, what Firefox is doing is saying, look, even though we're enabling it by default, we're giving enterprises an opportunity to disable it if the network signals to the browser that we're doing filtering, so don't use DOH. So how they do that is they created this application-dns.net host that it'll look up. So the browser will look up that host, and then depending on the response, if you own the DNS server and you respond with a no error, then that'll signal whether or not the client should use DOH or should use its local DNS servers configured in the OS stack. So this is something that today everybody should be doing until they figure out how to solve this problem long term, right? And Firefox says this is just a temporary solution. We're doing this until the industry agrees on how to address this problem. But again, they're giving you an opportunity to signal to the browser, do or do not use DOH. But only if it doesn't have the manually enabled flag, right, in the browser. So if a user decides, I want DOH, then this isn't gonna change, keep them from doing it. It's only the automatic enabled flag that is affected by the Canary Domain. Okay. All right. So this part's a little bit fun. I thought that I'd add this in here because there's some pretty cool things you can do with DNS, and CloudFlare lets you send an email, right? In this case, I sent an email to lookup@resolver.email, and utahhouse52.com. I said a record, utahhouse52.com, and within, in about a minute, I got an email back with an IP address. So out of band resolution for that IP address. Another kind of a cool thing, a couple of cool things is, how many of you guys use Telegram or know what Telegram is? It's a secure messaging platform, and you can add a friend in Telegram, and that's the quad 1 resolver, and you send it a message and it'll respond back to you. And similarly, you can use text message if you wanted, right? I send a text message and I get back the resolution for that domain. So it's pretty cool. Let me show you just a little quick demo. Hopefully this works. Do you see it there? Okay. Accept. Okay. All right. You know what I need to do real quick is, wow, that's because that's hard for me to see. I need to mirror my screen. Maybe I can do it. We'll see. Maybe if I make it. Let me try to make it. Okay. So there are Python libraries out there and applications. So this was Facebook has an open source Python library for DOH, and so I downloaded that, I installed it, and so it was easy to do. And so if I do this resolution here, I think for gambling.com, is that what it was? But I'm not on the right. Where's my, there you go. So this is real time, right? So I get an IP address. Hang on just a minute. Let me go ahead and mirror my screen so I can see it, because that little screen up there is not good enough for me. All right, there we go. All right, this is better. So we can see here, I ran this just for two things. First of all, I put in the time command in front of it. So if you, in case you're wondering, you can time any command you run from a CLI. So you can see how long it takes, and that's what this down here is. It tells me that it took, sub-second to do this resolution for gambling.com using the DOH client, and that went against CloudFlare 1001. But what's interesting is, so on my client, I have Cisco's AnyConnect running, and what it's doing is it's doing roaming security, and it's protecting my DNS lookups. So but we can see here we got gambling.com, this IP address. But if I did time dig gambling.com, so if I did this natively on the client without using DOH, I get this IP address. And if I do a dig -x for that IP address, okay, so Umbrella would have blocked that request, right? So it resolved actually to a block page using the native stack, but using the DOH client, it resolved to the real gambling.com address. So just an example here of how that works. And so I'm going to go back to the presentation, I think. All right. So, all right, what can we do about this stuff? Right. The first thing you can do is we can decide, hey, maybe we'll just abandon DNS-based security, and we can trust or rely on our firewalls to do application layer firewalling, server name indicator, leveraging a field in the TLS request that's in clear text to be able to determine what site that the user is going to. And the other thing we can do with TLS 1.2 and below is we can actually spy on the certificate exchange, where when they're negotiating the encrypted channel in TLS 1.2 and below, you can see the certificate that comes down from the server, and you can act based on that information. But there are a couple of problems with TLS 1.3. First of all, that certificate exchange is moved from the clear text portion of the communication into the encrypted portion. So they do a Diffie-Hellman exchange initially, and so they have encryption keys that they generate through that exchange in order to then encrypt the actual security certificate exchange. And the other thing that's happened with TLS 1.3, it wasn't in their original standard, but since then there's been an extension that is still draft, but it's coming, where they're going to encrypt the SNI, the server name indicator. And so you might think, well, we're dead, right? There's no way to solve this problem. But I don't think it's quite that bad, and I'll explain to you why. All right. So SNI encryption is dependent on DNSSEC being implemented, because the way SNI encryption is supposed to work is that there's still an SNI in the TLS 1.3 header, but it's encrypted. And the way what's supposed to happen is the client does a DNS request and gets the public key of the server that it's trying to communicate with over a secure channel, and then it encrypts the SNI using that public key. And so then the server would have to decrypt the SNI in order to determine whether or not, what domain, what URL the user is actually trying to get to. But again, remember what I said earlier, DNSSEC is not very broadly deployed. I think that there are years of runway still between now and when DNSSEC is deployed. Encrypted SNI is not ratified as a standard yet, and so there are lots of hurdles to get from here to there. But it's important to know that it's coming, right? So we can plan for it before it comes. The other thing is that there are a lot of people, you go read around online and they say, well, you can't do man in the middle in TLS 1.3. Well, that's not true. TLS 1.3 can be man in the middle just like TLS 1.2 could have, right? If the client, if they get the untrusted message, if they say ignore or move on, then you can man in the middle of them. Or if it's an enterprise or corporate device, and your certificate, you trusted certificate is on that device, so you can man the middle of that, again, the same way you could today. But with ESNI, that will get a little bit trickier with encrypted SNI, so that's where we'll see what happens as we get closer to that. Right. So, conclusion here is that DNS is one of the core protocols, right? It's not going away. It's just how it's going to be used is going to be modified. But I don't think that we should abandon DNS-based security, because it provides a layer of security that, first of all, will protect applications outside of just web traffic, right? So, and also DNS, we shouldn't abandon it because layered security is still the right thing to do. And maybe we're not going to get 100% of the users' traffic using DNS-based security, but if we abandon it, then we're giving the bad guys another avenue to do whatever they want to do. So, but again, it is going to be fully encrypted, but if that full encryption is to your server or your service provider or where you have control over, then so what? That's not a bad thing. It's providing privacy, but it's still allowing you to have control as an organization. And so I think that's all I have. I appreciate it. I hope this was informative for you guys. And if you have any questions, you come up to me and ask me afterwards. But thank you very much. Appreciate it.